Hi everyone, today we're going to talk about power, energy and work. So we will start with work. Work is force applied over distance, it's measured in joules and it's a scalar. So work formula is work equal force times distance cos theta. So let's look at an example. What is the work done on a 45 kg box that is being pushed with a 100 Newton force for 5 meters? So we'll reduce this equation to find work done or to find work. So we have the mass, as we have the force, and we have the distance. So in this equation, we are calculating force and distance and cos theta, which is the angle to find work. As in here we don't have cos theta, so we cancel it because you can't see it. So let me draw that for you. So it's a box with a 45 kg, which is its mass, is being pushed with a 100 Newton force for 5 meters. So it didn't say for us what direction it move, but we would know that it's a perpendicular direction to a perpendicular force direction. Well, because in here the cosine says is the angle between force and distance. We know the force would apply in this direction, let's say, which is 100 Newton, and the distance will be 5. So they move at the same direction and the angle between them is 0, so we would just cancel cos. So we would times 100, which is the force, by 5 meters to get 500 joules. So the second example says, how much work does the force of gravity do when a 50 Newton object falls a distance of 10 meters? I would like you to try it by your own, but for now I would answer that. I will work it out. So how much work? We're finding work and we know the equation for work, which is work equal Ft cos, which is force distance times cos theta. Does the force of gravity do when a 50 Newton, which is the force, object falls a distance of 10 meters, which is the distance. So what we're looking for is work, as we said. So we will times 50 newtons by 10 meters to get 500 joules. Energy is the capacity for doing work, and the equation of energy, as we can see, is a half times mass times velocity squared. So, and we have a different theory that says work energy theory. The change in energy equal work. So this equation, or the work energy theory, says that work equal delta energy, which says we know delta means final minus initial, and what is it? So it would be the final energy, which we know that for this the half doesn't change and the mass doesn't change because we won't change the object, we're just changing the velocity, and it would be the same here, but it would be initial velocity, vi squared with minus them because delta says final energy minus the initial energy. So let's look on this example. So it says a catamaran with a mass of 5.44 times 10 to the power of 3 kg is moving at 12 knots. How much work is required to increase its speed to 16 knots? 1 knot equals 0.51, and we know that this unit isn't the SI unit, so we need to convert those final and the initial velocity. So what we're going to do, we know that we have those two, as it says in here, we want to know how much work is required, and we know that both equations that give us work, which is those two, as the work equation and the energy theory equation. So, work energy theory equation, sorry. So we have the velocity and we have mass, and we know in here we don't have velocity as we also need force, and the question doesn't give us force or the distance, so we won't use the first equation and we'll use the second equation because we have both velocities and mass. So we have mass and we have the initial velocity and the final velocity. To convert it to an SI unit, what we're going to do is 12 knot we would times it. Sorry, my handwriting is really bad, I'm really sorry. So we know if we put knots in here, it will cancel because we know that there's an 1 in here, and we know the top and the bottom one cancels, so this unit will be cancelled, and we want it to be meter per second, which is the velocity. So we would end up with this unit, and we know that 1 of knots equals 0.51 meter per second, which is the velocity, and then you will get 6.12, and it's the same doing for the final velocity. And then putting a half, and then the mass, which is 5.44 times 10 to the power of 3 times 6.12 squared, because here you have final velocity squared, minus a half and the mass, and then times 8.16, which is the initial velocity squared. And so power is the rate at which energy is transferred, and it's calculated in watts. So we have the equation of power, you can see in here, which power is equal to work divided by time. And if it was split, and we know work equal Ft times cos, but for now we will ignore cos, we will ignore the angle, so we will just put force times distance and time, and we know distance and time, which would give us velocity, because we know velocity equal to change in distance divided by change in time. And so that would leave us with force times velocity, which is P equal Fv. And we can use this equation for power because we really know that we have an equation that says work equal delta energy. And so we can change work, we can replace work by delta energy, or we can replace delta energy by work. So let's try this example. What power does a pump develop to lift 35 liters of water per minute from a depth of 110 meters? 1 liter of water has a mass of 1 kg. So as it says, we want power. So we know the equation of power, which says power equal work divided by T, and we know work is force times distance, or displacement, sorry. So we have the mass. We can convert 35, as it says that 1 liter of water has a mass of 1 kg. So 35 liters is the same as we say the same as 35 grams. So, and the force. We need force. How did I get 343.35? It's by timing this number by 9.81, which is the gravity, as you can see in here. F equal ma, which is Newton's second law, which says 35 kg times 9.81, which will give you 343.35 Newton. And we have the displacement, as it says, 110 meter depth, and we have time, because it says per meter, and we know 300 liter of water per minutes. We know 1 minute is equivalent to 60 seconds, so that's why we put 60 seconds, because we want to convert it to an SI unit, and that will give us 629.5 watts. So this is an extra example. So a sailor pulls a boat a distance of 30 meters along a dock using a rope that makes a 25 angle with the horizontal. How much work does the rope do on the boat if its tension is 255? So we want to find how much work. So we know the equation of work, which states work equal force times by distance times cos theta. And we have the angle, which is 25, so we can use cos theta. So what we're going to do is 255 times 13 meters and cos 25, which is the angle, which would give us 6,117.6 joules of work. So the force P displacement graph below represent the force applied when moving a block through a displacement of 1.5 meter, which is the work done on the block by the force. So you want to find the work done by the block on the force. So we know the way we can see that this is a triangle, and to find an area of a triangle, which would give us an half times base times height. So replacing base and height, we will replace base with either force or displacement. So we know the base is just displacement, so it will be D. And we know the height, which is force, which would be F. Or we can even swap them. That won't make any change, sorry. And so we would a half times 20 newtons, which is the force. You can see 20 Newton, and then 1.15 displacement, which would give us 15 joules of work. An 875 kg car speeds up from 22 meters per second to 44 meters per second. Calculate how much work is done on the car to increase its speed. So we want work done. We know we would use work equal delta energy, because we have both velocities, and we want to see the delta between them, or the change between them, sorry. And so a half times the mass, which we have is 875 kg, times the final velocity, which is 44 meters per second squared, don't forget the squared, minus a half times the mass, which is 875, times the initial velocity squared, which is 22 meters per second squared, which will give us 635,250 joules, or you can write it as 6.4 times 10 to the power of 5 joules. And thank you for listening.